this video, we will understand about the magnetic properties of the transition metals. In order to understand the magnetic properties, we firstly consider some general phenomena that are related with the magnetic properties. The first phenomenon is the diamagnetism. In this phenomenon, the compound is repelled in the magnetic field, and such a phenomenon shows when the compound possesses no unpaired electrons. It means all the electrons are when paired, then the compound is repelled in the magnetic field and it is called diamagnetic. The another is paramagnetism. When a compound is attracted in the magnetic field or it get attracted toward the magnet. Such a phenomenon is found when the compound possesses unpaired electrons, and due to presence of unpaired electrons, the compound is attracted in magnetic field and it is called a paramagnetic compound. The third phenomenon is the ferromagnetism. Such type of phenomenon is generally found in the iron, cobalt and nickel. Such compounds are strongly attracted in the magnetic field. They also possess unpaired electrons, but in this case, the magnetic field, when the compound is kept in the magnetic field, the spin of all the metal ions get aligned in the same direction. It means the spin of all the electrons get in the same direction. So, the compound is strongly attracted in magnetic field. The fourth phenomenon is the antiferromagnetism. What is this? As from the name anti, it means it is strongly repelled in the magnetic field. It also possesses unpaired electrons, but in the magnetic field, the spin of all the metal ions get aligned in such a way that they get paired up. It means all the spin becomes paired, and so the compound is repelled in the magnetic field. Now we comes to the magnetic property of the transition metals. This is the electronic configuration of transition metals. As we know, in transition metals, the electrons are filled in the penultimate d orbital, and these are the electrons that decide the magnetic property of the transition metals. And it is also should be noted that in the case of transition metals, the magnetic property greatly differs when it is in the free state or in the elemental state, or when it gets complexed with the ligands. Firstly, we see the magnetic property of the free metal ion. It means when the metal is in the free state, it has not been complexed or it is in the elemental form. Then most of the transition metals shows paramagnetism, and this is due to the presence of unpaired electrons, because the electrons are being filled at each level. These are filling in the d orbital. This is the first transition series. These all are the elements of first transition series. As you can see, at the first level, this is one electron. Then in the titanium, there are two electrons, two unpaired electrons. In vanadium, 3. In chromium, 4. And in manganese, 5 unpaired electrons are present, and this shows the highest paramagnetism. There are highest unpaired electrons. Then in the iron, there are 4 unpaired electrons, and in cobalt, 3. In nickel, 2. In copper, there is 1 unpaired electron. But in the case of zinc, all the electrons are paired up. So zinc does not show paramagnetism. It is a diamagnetic compound. So the magnetic property depends upon the number of unpaired electrons. And we can say in the zinc, in cadmium and in the mercury, they all shows diamagnetism. Their +2 ion shows diamagnetism because all the electrons are paired. Here one thing should be noted, that in the case of mercurous ion, it means in Hg+, it is diamagnetic. It should be paramagnetic, but it is diamagnetic because it is present as a dimer. It means there are 2 ions. So the spin of both get paired up and it is present as dimer. So it is diamagnetic. The number of unpaired electrons, greater will be the paramagnetism, and hence greater will be the magnetic movement. For the free metal ion, the magnetic movement is given by the contribution of spin angular momentum and the orbital angular momentum. because there is spin orbital coupling. So the total magnetic moment is given by the under root 4s s plus 1 plus l plus 1, where s is the spin quantum number and l is the angular quantum number or orbital quantum number, and bm is the Bohr magneton. Metal complex, it means when the metal get complexed, the orbital contribution to the magnetic moment is usually quenched. It means it becomes equal to 0. Why? Due to the non-spherical environment. About this quenching of the orbital contribution, we will study later. Firstly, we see that in such cases, the magnetic moment is usually given by the spin only formula. What is this formula? That is mu s is equal to under root 4s s plus 1, or it may be under root n plus 2 bm, where n is the number of unpaired electrons, s is the spin quantum number, and bm is the Bohr magneton, that is the unit of the magnetic moment. The Bohr magneton is given by the formula E h bar upon 2me, where h bar is equal to h upon 2 pi, E is the charge of the electron and me is the mass of the electron, and all of these are constant. So its value is equal to 9.2 into 10 raised to the power minus 24 joule per Tesla. Now one thing should be noted, why this is the change in the behavior of the transition metals when they get complexed with the ligands, and this can be explained on the basis of the crystal field theory. What is crystal field theory? According to the crystal field theory, when the metal is in the free ion, when it is in the free state, it has not combined with the ligand. All the 5 d orbitals are degenerate, it means all have the same energy. So the electron get a path for the rotation around the nucleus and it forms the orbital angular momentum, and hence the magnetic moment is resultant of the spin and the orbital angular momentum. But when the ligand is complexed with this metal, it means when the ligand comes near, the degeneracy of these 5 orbitals is removed. It means the 3 of these d orbitals, that are dx, dy and dz, that get lowered in energy, and these 3 are degenerate, so they are called T2g orbitals, while 2 another, that are dx square and dz square, get higher in energy, and this forms the EG set of the orbitals. So we get 2 different sets, that are T2g and EG, and there is a difference of energy between these 2 labels. Now 2 things can be happen when the ligand is strong field. It means it is high field ligand similar to cyanide or CO, carbonyl. These are strong field ligand, and these can cause the high splitting of these d orbitals. It means the energy gap between these 2 levels is very much higher when such a ligand is complex to the metal. So the energy of T2G level is very much low, while that of EG level is very much high in the case of octahedral complex. We are taking here octahedral complex in the consideration. So the energy required to jump the electron in this level is very much higher as compared to energy that is needed for pairing the electrons in these levels. So the electron wants to pair up. It means they firstly get fill in this T2G level, and then they pair up, and then they comes to the EG level. So the complex that we get is of low spin type. It means the maximum electrons get paired and we get a low spin complex, and such complexes are mostly diamagnetic. Now we see the case of weak field ligand. When the ligand is weak field, such as chloride ligand or oxide ligand, in such cases the splitting is very small. The energy gap between these 2 levels is very small. So the electrons can easily jump to this EG level, and the electrons firstly go to T2z level, then go to Eg, and then they pair up. So we get a high spin complex. It means maximum number of electrons remains unpaired, and we get a paramagnetic complex. So this decides that whether a compound will be low spin or high spin. We can see it with the help of an example. If we take the iron and we take its two complex, one is this type of complex, that is FeCN6 minus 4 charge. This is a complex with the strong field ligand, because cyanide is a strong field ligand, and it causes a large splitting of the two levels. This is a large splitting. So the electrons all get paired up in this T2z level, because it requires higher energy to jump in the Eg level. So all the electrons get paired in the T2z level, and the mu s, it means the magnetic moment spin only formula, we get under root n plus 2, and it becomes equal to 0 because there is no unpaired electrons. So this compound is diamagnetic. And if we see another compound, that is FeH2O whole 6 plus 2 charge. In this compound, water is present as a ligand, and this is a weak field ligand. So it causes a small splitting, very small splitting of these two labels. So the electrons can easily jump into the Eg level, then becoming the pair up in this level. So we get this type of structure. It means 4 unpaired electrons are present here. So the magnetic movement is given by under root 4 plus 2, that is 4.90 bm, and such a compound is highly paramagnetic. The 4D and the 5D series, the magnetic moment is given by the spin and the orbital contribution. But in the case of first transition series, the magnetic movement is generally given by the spin only formula. But there are some cases like low spin Fe plus 3 ion, high spin Fe plus 2 ion, CO plus 2 ion. In these cases, the mu effective or the magnetic moment that is observed is usually greater than the mu s. If we see the transition series carefully, then we find that for the D1, D2, low spin D5, high spin D6 and D7 complexes, mu effective is greater than the mu s. Why? Because in these cases the magnetic moment is given by the combination of both the spin and the orbital angular momentum. So why it happens that in some cases we get the magnetic moment by only spin formula, and in some cases we use both the spin and the orbital contribution? The reason for this is that the orbital angular momentum generates due to the rotation of the electron around the nucleus, and this rotation happens via the orbitals. It means this is a nucleus and the electron rotate around this nucleus, and it is present in the orbitals. So it will rotate via the orbitals around the nucleus, and when it rotates, then only the orbital angular momentum generates. If there is no path for the electron to rotate, then it cannot produce the orbital angular momentum. So in most of the metals, this angular momentum is usually quenched. Why? Because of the restricted rotation. It means the rotation of electron is restricted because it does not get the path for the rotation. This is somewhat due to the shape of the d orbital and somewhat due to the effect of the ligands or the outer environment. So for the orbital angular momentum to contribute, there must be one or more empty or half filled orbitals similar in energy to that of the orbitals occupied by the unpaired electrons. Such a orbital should be present for the orbital angular momentum to contribute, and this orbital should be of the appropriate energy. It means its energy should be similar to that of the orbital that possesses the electron and of the same symmetry. And this orbital should not possess the electron of the same spin as that of the rotating electron. so that the electron can use this nearby orbital to circulate around the nucleus. It means it provides a path for the electron to circulate around the nucleus, and in this way it can generate the orbital momentum. For example, if we see these two orbitals, this is dx square minus y square orbital, that is we have denoted by the black color, and this red colored is dxy orbital. Now these two orbitals are of almost similar energy, and this can be transformed by rotation around 90 degree. So these provide a path to the electron for the circulation. This blue colored line shows the circulation of the electron when we apply a field perpendicular to the xy plane, and this orbital should not possess the electron of the same spin, so that this electron can move by this orbital. T2z orbitals, all the T2z orbitals dxy, dxz and dyz are degenerate and have the same energy, shape and symmetry, and they can be transformed into one another by rotation around 90 degree. So if we see the D1 and D2 configuration, in D1 there is one electron present in T2z level, and these two orbitals are vacant, so the electron can use this orbital to rotate around the nucleus, and in this case there are two electrons and this orbital is empty, so the electron can rotate via this orbital. So these two makes the contribution, orbital contribution towards the magnetic moment. While in the case of D3 configuration, there are 3 electrons in the 3 T2z orbitals. So all are of similar spin. So there is no vacant T2z orbital. So there is no path and hence no orbital contribution. And in this case, the magnetic moment will be given by only spin formula. In the low spin D5 configuration, this is the stage of the T2z level. There are 4 electrons and 2 electrons in this orbital. It means 1 electron with the inverted spin in this orbital, while in these 2 orbitals there is no electron with the inverted spin. So it provides a path for this inverted electron to rotate, and this makes a contribution, orbital contribution toward the magnetic moment. Similarly, in the high spin D6, there is 1 electron with the inverted spin in this orbital, while these two do not have. So it provides a path for this electron to rotate. Similarly, in D7 configuration, these two have two electrons. It means this one with the inverted spins and this do not have. So it provides a path for this electron or this electron to rotate around the nucleus. So all of them will make the orbital contribution toward magnetic movement and will have the magnetic moment higher than the spin only formula. But when all the T2z orbitals are singly or doubly occupied, it means there are 1 electron in all T2z orbitals or 2 electrons in all T2z orbitals, then there is no path for the rotation of the electron. So they will not make the orbital contribution toward the magnetic moment. So the mu effective will be equal to mu s. It is also affected by the geometry of the complex. Which type of geometry the complex is taken? For example, if we see the nickel plus 2 ion that has D8 configuration, in the free ion state, it has both L and S coupling. It means its magnetic moment is given by the combination of both the orbital and the spin contribution, and it will be equal to 4.47. But it when makes the octahedral complex, this is the splitting in the octahedral complex, and these T2z levels all are filled completely. So there is no path for rotation, and this complex do not make any orbital contribution toward magnetic moment. So its magnetic moment is given by spin only formula. Now when it makes the tetrahedral complex, as you know, in tetrahedral complex the splitting is inverted. It means EZ level is downward while the T2G level is upward. This is highly in energy. So this type of configuration is found in the tetrahedral complex, and this is the T2G label. You can see there is 2 electrons in this orbital while 1 in these 2 orbitals. So this electron with the inverted spin can find a path to rotation via this orbital or this orbital. So it can rotate and it makes a contribution towards the magnetic movement. So there the mu effective will be greater than the mu s. It is higher. So by this we can easily see that which will be the magnetic moment, how much magnetic moment a compound will have when it is complexed or it is not complexed. So you can easily determine by this. Thank you for watching this video. If you like this video, please share, please subscribe. If you want any more topic, you can send us.